Yes. Right. EDTA is a coordination number 6. No. It would be called hexadentate. Yes.
Why do they put ETA? ETA compounds like soap.
EDTA might be put into soaps, and I'm just guessing here, is because of hard water. You know, what happens is a lot of soaps will precipitate with hard water to form soap scum, and so EDTA will attack the hard water ions, which would be like calcium and the bigger cations to make the soap last. And so a lot of soap is actually wasted because of hard water, I think. But there might be other reasons. Are you taking the? We're going to take the quiz at the end, and so today's plan is we're going to talk about the lab a bit, and then you're going to finish the lab, and then the quiz isn't very long, so you'll have maybe the last 35 minutes or so for the quiz. All right, any other questions from chapter 24 or whatever? Is it out? Uh-huh. The only problem with taking the quiz first is that some people finish the quiz in 5 minutes, and other people finish in 35 minutes, and so there's a huge discrepancy in when people finish. So rather than making the people wait a long time, that's it. But you'll have a break before the quiz, so you know whatever short-term memory you might lose between now and then, you can refresh in your memory. And so you have like a 15-minute break before the quiz. All right, for the synthesis lab, you're going to write a formal scientific report. You know, how many people have written a formal scientific report? And so, for those of you who haven't, it's just organized in a certain way. And the way these reports are organized is the first section is what do you write as the first section? The abstract. Have you guys heard of an abstract? Can you describe what an abstract is for me? It's not really a preface. It's a little more than just a preface. You know, preface is kind of like we would call an introduction. This is more of a yeah, it's a summary. It's a one-paragraph summary or synopsis of the experiment. Most people don't want to read the whole report. Most people will just want you to tell them in one paragraph everything they need to know about what you did and what you accomplished in this experiment or series of experiments. And so, you know, all your key results should be in the abstract, your key findings. That way, I think 99% of the readers will never make it beyond the abstract. 1% of the readers will be actually interested, really interested in what you did, and will will want to read the whole paper to get all the little details out of it. And so abstracts are very important in science because everybody's overwhelmed with too much stuff to read, and they just want to focus on the most important things to read for them. And so let's take a look at this abstract and see if this is a pretty good synopsis of this synthesis. The title here is not that great. You want some key words in the title. So this person just used synthesis lab. Let's take another look at a title. This title is kind of vague too. We look at this title. This title is synthesis of cobalt-3 coordination compound. Depends, but you know, title I'm not really going to worry. Some places you can only use certain words in your title, and the reason for that is so that they can put it into a searchable database. And, excuse me. And so this is the synthesis lab. The abstract's one paragraph, so it's just this first paragraph here. The second paragraph's not the abstract. And so a lot of abstracts, what they'll do is they'll block it off. That is, they'll indent here and then use a different font size, maybe bold, just to make it look different than the rest of the paper. In a lot of journals, they have a word limit, but I'm not going to have a word limit. But you shouldn't go beyond one paragraph, though. The purpose of this experiment, and one other thing, abstracts aren't supposed to contain figures. You're not supposed to put any figures or equations in abstract unless the equation is the central part of the paper. Then you would put it in there. But this is a synthesis lab, that's correct. The purpose of this experiment was to synthesize this. How would you name this? It would be sodium hexanitrito N cobaltate 3. Good. Would this be trisodium or just regular sodium? Yeah, just sodium. Good. And so we're going to synthesize. This particular semester we synthesized the cobalt complex, and we use a different procedure than the one in your lab manual. So I handed the procedure out on this one. From 2.5 grams of this, how would you name this? Hexa-aqua. Hexa-aqua dinitro? No. Yeah, nitrate's outside the coordination sphere. So it's hexa-aqua cobalt or cobaltate? Cobalt 2. Yeah. Nitrate. Yeah. So the anion name would just be nitrate. This one's easy. What's this one? Sodium nitrite. All right, first the cobalt compound and the sodium nitrite were both dissolved in 8.0 milliliters of water. Then the solution was cooled to below 20 degrees Celsius. 5 milliliters of 50% acetic acid solution was added to the solution inside of a fume hood and allowed to react. Afterwards, air was bubbled through the mixture for 30 minutes where the oxygen in the air reacted to oxidize cobalt-2 to cobalt-3. Then the solution was cooled, and with continuous stirring, 15 milliliters of ethyl alcohol was added. The ethyl alcohol precipitated out the ionic compound, The solution was covered in parafilm and sat for 2 days. Then the crystals were filtered using ethyl alcohol to wash out the crystals and obtain as much as possible. 0.19 grams of the complex were obtained for a 5.84% yield. A 5.8% yield, is that very good? No. But you don't have to worry. If you get a low yield, no big deal, because I'm most interested in purity, not in terms of quantity. And plus I'm not paying for the chemicals. If I were paying for the chemicals, I'd probably want a better yield, right? Well, maybe I am paying because everybody pays for your taxes. And so not the greatest yield, but it's fine. They weren't They weren't penalized at all for that yield. Let's take a look at this abstract. Here they just say this much product, let's say, was obtained and dissolved. Oh no, this much reactant, 8 milliliters, 50% glacial acetic acid was added. Solution was oxidized in the oxidizing apparatus for 30 minutes, and NO2 was trapped. Afterwards, it was filtered and added dropwise 15 milliliters of ethanol. It should be ethanol, not ethanol alcohol. It's either ethanol or ethyl alcohol. Until yellow-orange crystals were formed. This is good. They put some colors in here. It's always good. You know, did you know it was orange, yellow from the previous abstract? No. The solution was filtered using the vacuum pump apparatus. 3.47 grams of solid was obtained. A synthesis of this from that gave a percent yield of 92.2%. A huge difference in percent yield. This is the same semester, same class. Makes me wonder if there's a calculation error or they just lost a lot. All right, after the abstract comes the introduction. The introduction is a little bit like a preface. What you do in an introduction is you give a little bit of history, you know, what's happened in the past, you know, where are we at now, kind of thing. But, you know, what's happened in the past and where we are now can focus on all aspects of the experiment or just on specific aspects of the experiment. And so the things that, like, for example, here, if you look at this introduction, chemical synthesis is defined as the production of a substance from simpler materials after a chemical reaction. The synthesis is produced by the reaction of the combination of the chemical elements, groups by the degradation of a complex compound. Actually, I don't know what that sentence means, but it should be rewritten. Chemical synthesis involves the breaking of existing bonds to form new ones. That sounds good. The synthesis of a complex molecule may have several reactions that lead in sequence from the starting materials to the desired product, as in this case, but they didn't say that. One of the goals of a chemical synthesis is to produce a high. So this person spent time talking about synthesis because you know, that was the focus of the experiment. But, you know, in other introductions, we'll talk about, you know, what the heck do they use this for? You know, why are we synthesizing this? Is there any practical application to this compound? You know, or other people might focus on, you know, who was the first to do this synthesis? You know, this synthesis was first done in 1878 or something like that, or, you know, by whomever. And so, you know, or abstracts can focus on a technique, you know, if you're looking at a certain type of technique. Not abstracts, introductions. And so let's take a look at another intro here. This intro is a little longer and hits more topics. And so you just do some research. You're welcome to, you know, copy and paste things, but if you do copy and paste things, make sure it's clear that you did copy and paste it. Otherwise, it would be plagiarism. So be careful with that. And make sure, even if you use some information, you should cite the source of that information. So, but synthesis, we don't have to cite the source of that. Synthesis is so common. Synthesis reactions are often used commercially by chemists to obtain a certain product or intermediate product. That doesn't need any citation. That's just common. The series of reactions in this experiment was intended to synthesize our desired product. But this product is special in that the type of molecule created is known as a coordination compound. And so here, coordination compound, they're starting to talk about that. Coordination compounds or complexes consist of a metal center bonded to a species called ligands. And so this is good, you know, a good introduction, talks about coordination compounds, complexes, ligands, and metal centers. Ligands act as Lewis bases when reacting with metal and donate electrons to the central metal. The coordination number of a complex indicates how many points ligands are capable of bonding to the central metal. Some ligands are capable of donating electron pairs from multiple atoms on the same molecule. These ligands are called polydentate ligands because they bite the central metal at more than one point. And so giving some background on complexes, let's see what the next paragraph says. Coordination complexes were first proposed by Swiss chemist Alfred Werner, who said that certain metal atoms had two types of valence electrons. Primary valence for when a metal atom became an ion, and secondary valence, which determined how the atom bonded with the ligands. Much of Werner's work centered on the study of isomers, and it was he who proposed that metals with coordination numbers of 6 would have octahedral structure, and prepared many optical isomers, including the first optical isomer lacking carbon called hexol. Here, we definitely need to cite the source of this. And this is starting to talk about, isomers and structure. Have we really talked about, no, that's going to be in chapter 24, part 2, so we jumped ahead in there. You don't necessarily have to talk about this. They go on with isomers. Isomers are two different molecules that have the same formula, and so they spent a lot of time going through isomers here, and this is just from our book, basically, which is fine, cis, trans, isomers. But we really aren't doing anything with this, right? We're just doing the synthesis. So this one is starting to push the boundaries of what should be. This is more like space filling. Right? Some people are worried about, how many pages should the report be? There are lots of others. Okay, after the introduction section, again, it just gives some historical perspective or some background information on whatever, Both of those introductions, what a lot of people do, and I didn't bring these papers in, a lot of people will talk about the specific compound they're trying to synthesize. This is the structure of the compound, this is the uses of it, what are the unique features of that particular compound. And then we know why anybody would want to synthesize it. All right, after the introduction comes the experimental section. The experimental section is, your recipe, your specific recipe, not the recipe that's given in the lab manual, but the recipe that you actually used, with the amounts that you used. And so if you're baking cake, but you had some slight variations from the recipe, if somebody wanted to repeat, what you made, exactly how you made it, then they would follow your recipe. And so your recipes, one thing is it's always going to be past tense. And so like here, first my partner and I measured out 2.5 grams of the reddish orange solid. Some things aren't really that necessary. First my partner and I discussed for 3 minutes, who's going to weigh this. I don't want to hear that. And then we walk together to the balance. Yeah, you could leave that out. You just have to have, if you want some kind of guideline of how much detail you need to put in the experimental, you just have to imagine somebody being able to repeat this exactly like you did it. Does that mean that they have to use, well, I used a 250 milliliter beaker, but if somebody used a 300 milliliter beaker, would that make any difference? And so we would leave out that detail, we just say measured out this. And then they can use whatever beaker they want. They could use a 600 milliliter beaker because it makes no difference. But some people like to put that in here. Also note that there's no equipment lists. Lists aren't allowed in reports because lists, equipment list, chemical list, that kind of thing, takes up a lot of space and is a waste of paper. So most journals do not allow lists in the experimental section. Unless, you're repeating experiments over and over. It's the most compact way of showing it. But let's read this one. Obtained. It probably said obtain, in the procedure, but they want to make it past tense, so they say obtained approximately 2.5 grams. I don't want to hear approximately 2.5 grams. I want to know exactly how much you got, what balance you used, how many sig figs. And so, this shouldn't say 2.5. This should say something like 2.53 grams, and so we don't want approximately. Just tell me. From the stock room, and it was dissolved using 8.00 milliliters of deionized water. 8.02 grams sodium nitrite was weighed, not weighed. It should weighted. I see this all the time. It's not weighted. You know what it is? Just weighed. Get rid of the T. Into the solid sodium nitrite. And the solid sodium nitrite was stirred into the cobalt nitrate solution until dissolved. The solution was cooled below 20 degrees C in a cold water bath. In the hood, 5.00 milliliters of 50% glacial acetic acid. Glacial acetic acid is about as pure of acetic acid as you can get. It's like a liquid. It's almost 100%. You know, you just can't get rid of that last bit of water that stays in there, but it's in the high 90s. Were added drop-wise, prepared with 5.00 milliliters of 17 molar glacial acetic acid and 5.00 milliliters of deionized water. Then the solution was transferred to the oxidation apparatus in Figure 1. So what's the oxidation apparatus in Figure 1? And so they added a couple of figures here, Figure 1 and Figure 2. Here. These are actually from the lab manual. These are hand-drawn figures. The solution was oxidized in the oxidation apparatus. You know, there are a whole bunch of little, typos or word things here, which, even though the writing center, they might not understand the science, but they can help with those types of things. And so you can bring your paper to them. They'll proof it for free. And I've had students do that, and the papers come out pretty good. For approximately 30 minutes afterwards, the solution was bubbled through the apparatus and trapped the toxic NO2. This is not detailed enough. I don't know what this means, bubbled through the apparatus and trapped the toxic NO2. And so there, there's a lack of detail, I think. Whereas, let's see what the other author did with the NO2. And so this author said this: the gas produced by the mixture was toxic NO2 gas. The toxic NO2 was fed to a flask filled 1/3 water, where the NO2 dissolved and formed nitrite and nitrate ions. And so, this is more the level of detail you want here. At least, how did you trap it? What did you use to trap it? It wasn't clear. So how can you repeat it, right? Let's go on here. This is just giving you the amounts, the times, all these things, and hopefully the colors of what you mix together. And so that's the experimental section. Any questions on any of these sections? The dates are a nice addition, but you don't have to have the dates in. Most people say 2 days rather than it started on September 18th, so September 11th, and ended on September 18th or something like that. All right, after the experimental section, comes the results and discussion section. In normal papers, the results section is separate from the discussion section. And so does anybody know what's the difference between the results section and the discussion section?
The discussion analyzes.
Yeah, the discussion analyzes the result. The results are the raw data. The raw data, is pretty much irrefutable. That's just the experimental results is fact. But how you analyze the raw data, that's open to discussion. That can be questioned. And so, as we always say, theory must agree with experiment. If it doesn't, then what's wrong? The experimental facts or the theory? The theory is wrong. Experimental facts are facts. And so we usually separate them. We want to keep the facts separate from our analysis of the facts. And that's often done in science so that As theory improves or as equipment improves, people can go back and look at old raw data with a new eye. Now we understand this about the theory, therefore this is what this means. And so in the literature, in the scientific literature, what you see a lot is reinterpretation, a paper that's called reinterpretation of so-and-so's results. We're going to combine everything so we don't have to worry about it. We're going to combine it into results and discussion. And so this is a synthesis lab, so we're most interested in what do you think is most important in a synthesis lab? Calculating the theoretical yield, is that the most important? Well, it's important, but not the most important. The most important would be the reactions, right? What were the reactions? And so this person's kind of started off backwards. Calculating the yields are what we usually do last. They did it first, but we always calculate yields last. This person did better to start with the reactions. So one of these is just the electrolyte properties of this complex. It dissolves in water. Yeah, it's a nitrate. All nitrate salts are soluble, right? When it dissolves in water, they just give you the aqueous species here. And so this is just electrolyte. And so you'll notice that in the discussion section, you verbally talk about and you show the equation. And so we'll talk about this, and then we'll show the equations. And so the first reaction here is oxidizing cobalt 2 to cobalt 3. Is that shown here? No, it's not shown there. Is it shown down here? No, it's still not shown here. So the way this is organized, I don't particularly like as much. This is a side reaction. This is a side reaction during the oxidation step. But what was the oxidation step? Well, here it is. And so they talk about this a little bit, but we could talk about it a lot. The oxidation process came during the bubbling process, and with the presence of acetic acid, simultaneously some side reactions happen. Okay, the NO2 is produced by some of the nitrate ions, disproportionate. And so in other words, we had some side reactions in the redox. These side reactions produced products. They weren't part of the main reaction, but they contributed to some of the main reactions. So this particular synthesis was complicated because multiple reactions were occurring at the same time, right? Our reaction is a lot simpler, a lot cleaner, because we didn't have multiple reactions occurring at the same time. And so the side reaction business is something that is particular for the cobalt lab. And so what was the oxidation, the primary reaction? The primary redox reaction for the oxidation was here. Cobalt 2 was oxidizing to cobalt 3 by using a stream of O2 in the presence of the desired ligands. It was observed that once oxidized, the solution went from dark red, violet, to dark orange. And so here's the redox. So we got our cobalt 2 complex, our acid and O2 being oxidized, the cobalt being oxidized to cobalt 3. In the process, we produce NO. Where does that NO come from? It's amazing. It's amazing because I write the equations on the board, but I'll tell you, 80% of the reports I see, I have no idea where they got the equation. No, like this equation here. This equation really bugs me. Do you know why? This equation really bugs me. One thing I cannot stand are equations that are not balanced. When I see it, and I see it right away, I see equations that are not balanced all the time, and then atoms can neither be created nor destroyed. It's so easy to check for balance, usually, but it's people aren't in the habit of doing that. And so where did these nitrogen atoms come from? You know, it just so anyway, there. I know what it is, because these equations aren't in the lab manual. The equations aren't in the lab manual, and they don't bother writing them off the board. Then they start making up a whole bunch of equations for the report. That's where they come from. And so every semester I see the same thing. And so if we look at this other report, it's the same. You know, maybe about 5% of the reports actually have the right equations in the right sequence. Some reports, they don't even bother writing the equations. Like this one, you know, this is crazy here. You know, in this first half reaction, we're producing hydrogen gas, you know. In the second half reaction, you know, both of these are oxidation half reactions, and somehow they add the two oxidation reactions and get a redox reaction. You know, there's no reduction here. And then somehow the hydrogen gas goes away, you know. But I know. I know what's going on. So anyway, I went through all the equations, but basically talking about the reactions, and you can talk a lot more. You know, you can talk about, you know, things like oxidizer, reducer, what makes that a particularly good oxidizer, or what makes that a particularly bad reducer. All these things, you know, that people can add, but they don't. And I don't understand why they don't add those in the paper, because, you know, those are points that could help strengthen their paper. You know, but for some reason it didn't click or catch on. And the same thing with the equations. For some reason, the equations didn't click or catch on. But this cobalt synthesis had a series of reactions: redox, Lewis acid base, and metathesis. I like this cobalt synthesis quite a lot. This cobalt synthesis is a little bit less clean than our chromium synthesis. You know. But anyway, by the end of the reaction, you know, we got, let's say, we have the same type of metathesis deal going here. You know, in the presence of ethanol, we're going to precipitate out this. So this is said verbally, and you can talk about this. You know, there's a whole bunch of things you can talk about for this one equation, right? And those are the types of things we add in there. And then we get to the end. This is our final product, right? Now, our final product, are you sure that's going to be your final product? You know, after going through this discussion, do you trust them to, okay, this is what they're telling you that they synthesize, but do you trust them? You know, and that's what you're going to run into when you write your discussion. You're trying to, you know, you're trying to convince somebody that what you're synthesizing is what you think you're synthesizing. Because most papers are in scientific journals, in fact, nearly all papers are refereed papers. That is, before they'll ever print it, they send it to 3 to 5 people to check, to act as referees. Now, referees, this is like jury duty. You know, if you're working in a particular field, you're going to get papers sent to you too, and you're going to be asked to referee them. And so what you do when you referee them is you just go through them and make sure that their reasoning is sound, you know, and that they provide ample justification for what they're. And so these guys have claimed to make this. And so by reading this discussion, do you agree that they made that? And so not many people do. In fact, nobody does. And so one of the sore points of this particular lab is this. If you look in the journals, most synthesis labs are not synthesis. Most synthesis labs consist of synthesis and characterization of whatever. And so what does characterization mean? Because that's something that's missing out of our papers. And so have you ever heard of characterization before? Characterization is just characterize your product. That is, prove that the product is what it is, and then also tell me what the purity of that product is. That's what characterization is. And so how can you characterize our product? Is there a way to characterize it? Uttima, do you know a way to characterize products? Like barium sulfate?
Barium sulfate is partially soluble. So if it dissolves, you can do different things.
Well, okay, you're saying maybe measure some of its properties, like color. Obviously if the color doesn't match, maybe that's a problem, or other things might not match. The crystal shape or the crystal form might not match. And so characterization involves some physical observation, looking at, does this look like the right product? Do you know what the right product is supposed to look like? In fact, what does this stuff look like? And is the stuff that you made the same? But, looks can always be tricky. Because when you look at something, it's hard to tell, based on color, because color depends on how big the crystals are, and what contaminants might be in there. And so we try to look for more ways to characterize these things. And one of the most common ways that you'll encounter in organic chemistry is by taking melting points. Melting points, because most compounds will have different melting points. Sometimes the two melting points will coincide, but if the melting points are different enough, then, we can see where this stuff melts. And so in an organic chemistry lab, what you do is you scoop some crystals into a melting point apparatus. There's a little telescope. This telescope focuses on the crystals, and then you ramp up the temperature. You watch the thermometer and see at what temperature does it liquefy. What temperature do those crystals melt? And then does it match with the melting point of the substance that you think it is, or that you tried to make? Right? All right, melting point can help you ID it. In addition, melting point can tell you a little bit about the purity of the substance. You remember that, Sutama? And so what is better? A wide-ranging melting point or a very narrow melting point for purity? You remember? Or Vaughn, do you remember? What's more pure? A narrow melting point or a wide melting point? Yeah, a narrow melting point is more pure. Because when you think about a crystal lattice, all the bonds are the same. And so all the bonds should break at the same temperature. And that's what happens. In a crystal lattice, all the bonds break, the crystal falls apart, and it melts. But if you have a lot of impurities in there, what happens is no longer are all the bonds the same. If there are impurities there, then some of the bonds are weaker, some of the bonds are stronger. And so as you heat it up, you break the weaker bonds first, and then the medium strength bonds, and then the strong bonds. And so it widens the range, and the wider the range, the less pure your substance typically is. Well, there's problems with melting point, because melting point, we can't go too high. A lot of these ionic compounds have a very high melting point. And so high enough that it requires a flame to melt them, and so it's not so practical. Are there other techniques of characterization? You may have to go back to chapter 2 or something for this. Yeah, density, you can measure density. Like fool's gold is easy to differentiate from real gold because of the densities are dramatically different. Right? Any other ways? Well, solubility can do it, but there are lots of insoluble things, lots of orange insoluble things, so it's tough. Daltons? the Daltons, the amounts of, I'm sorry, the,
The atoms.
oh, Dalton's, like, atomic theory, Dalton's atomic theory, that, you know, theories should be able to predict new results, and one of Dalton's atomic theory's new results that it predicted was the law of multiple proportions. And so, yeah, unfortunately, we aren't, it'd be kind of tough to apply. But anyway, if you still have Chem 1A book, take a look back at chapter 2, I think it is. You might find some other methods of characterization. It turns out to be a lot. All right. So that's one of the things about this. And so, you know, we'll see today. You know, how pure do you think this stuff is after the synthesis? The stuff you made that's sitting in your drawer, how pure do you think it is? 100%? Well, maybe. Maybe not. We'll see. All right. So in the discussion section, like I said, you're going to talk about the chemistry because, you know, by going through these steps, you know, we're doing this synthesis, we're doing this synthesis, we're doing this synthesis, then it makes sense, you know, as you follow along, yes, we should be making this, yes, we should be making that. And then we're washing it, oh, yes, it should be clean, free of impurities, right? And so we go through all these steps to make sure we have the purest stuff that we can get. Sometimes we want even purer stuff, and so this is why I asked some of you to redissolve it, because you know, there's a process called recrystallization. That is, you know, you crystallize it or precipitate it, and then you redissolve it and then reprecipitate it. Each time you reprecipitate it, it comes out a little bit purer because you discard the solution. The solution typically contains the contaminants, and so. You know, that's one of the things. That's something you can actually try yourself if you want. Take some of your crystals and try to recrystallize it and see what they come out looking like. But anyway, we just go on, and then finally at the end of the discussion we're left with this. You know, this is the product. You know, and we'll probably do our percent yield calculation here at the end, talk about it and that. But do we really have that? You know, when you look at your discussion, was it a convincing argument that we do have this in high purity? Think about that, because you have to argue this chemically. You can't just say, I think I have this in high purity because the book told me that's the product I'm going to get. You know, that doesn't cut it. You know, you have to have some kind of argument for it. Okay? Well, in short papers, this is considered short paper. We don't have a conclusion section. You know, there's no, you see no conclusion. And a conclusion is very different than what you might have done in other classes. You know, typically a conclusion is just a summary. Well, we don't need a summary because we got the abstract, right? So no reason for that. And so we can just end it as is, right here. Or what's typically done in a scientific paper for conclusion is not a summary. A conclusion is what you're going to do in the future or what you recommend somebody else to do in the future. And so typically a conclusion would be, if we had this instrument, or if we had unlimited money, or if we had unlimited time, we'd do this. Or we recommend that, you know, whoever does this should go along this path to get better results. That kind of. And so conclusion is a look into the future, you know, what you want to see. And so then the next authors are going to reference your paper in the introduction to their paper and then continue the work. You know, science is one of, you know, people building on top of other people's work continuously. You know, you don't develop everything from scratch on your own. All right? Okay, any questions on the formal report? That's so common in the conclusion, but it's not really, you know, a lot of people will say this. I read this all the time, but I think it's kind of worthless in some respect. So some people will say, I got a 92.2% yield. And so in conclusion, experimental error caused a 7.8% loss. Experimental error. people attribute all error to experimental error, then it's worthless. If you can't say specifically what the error was, then don't bother. And so what could have caused that loss? Well, maybe I lost, But if you come up with some generic statement saying, well, I lost a little bit here and a little bit there, it doesn't help anything. The experimental analysis goes in the discussion. It should be in, where you need it, up here, not at the end. But when you're talking about the numbers, that's where you talk about losses. Or when you're talking about a particular step in the reaction. Let's say at this particular step, I wasn't able to recover all the crystals. So no big deal, you're going to lose some. But at least we know, well, that inability to recover all the crystals means that you're going to lose some, right? Or in the filtration step, when you filter it, that's where you're going to talk about error, but not as a conclusion paragraph. Okay? That's just me. For your other class, do as your professor says. Don't do as I say, because they're the ones who are giving you the grade. Yeah, that was a question I was expecting. This is going to be due in 2 weeks. 2 weeks. That's not much time. But you should be able to. It's not that complicated of an experiment. Just three reactions, a whole bunch of other steps in there, right? So you should be able to whip this up in a. What I would do is I'd give yourself a time limit. Like say within 1 hour I'm going to have a rough draft of the paper. Within 2 hours I'm going to write a rough draft. And the next week, show me the rough draft, so I can take a peek and give you some suggestions if necessary. All right, so we'll have it due in 2 weeks, so it doesn't give you much time, but you have choice. The choice is you can work on the paper by yourself, or you can work on the paper with others, your friends or lab partners or whoever. And you can jump groups. So if you did the experimental work by yourself, you can write the report as a group. It'll be a co-authored report. Co-authored reports are very common in science. And so this one will be a co-authored report, and maybe we'll have an individual report. We're going to have 3 of these formal reports, so one of them I'll make individual. But not the first one. All right, so in 2 weeks it's due. So next week have some kind of rough draft, so I can look at it.
Do you think you can put these examples on the
I can't. I don't have permission. These are old reports. I can't.
Is there a basic format?
There's a basic format. I can put that on Piazza. Did I post it? The scientific report? I'll put it up on Piazza this afternoon. It just talks about the abstract, the introduction, the experimental section, etc. Those. I can't post these on Piazza, but if you want to see these again, I can bring them up. I have lots of old papers, and all of them, highlight different things. All of them have the, strong points and weak points, and they're different. And so, some papers I really like particular sections, others I don't. And so this paper here, both these papers I like because they wrote the chemical equations. Although this is wrong. This is a side reaction, and they didn't write the main reaction. They wrote the side reaction, but not the main reaction. Well, I guess this is the main reaction, but it's not quite right as far as the half reactions go. And so, yeah, those types of things. But if you get everything good, then, that's something I notice. And there are papers that they actually were paying attention to the reactions. And they got them good. For the paper, 2 to 3, actually 3, up to 3. What happens is, this happens every semester. You know, I have a 2-person group and 1 person drops the course, and then we triple up in another. So we'll go up to 3. Sometimes it's graded a little differently. If you work by yourself, you know, I'm a little less strict, a little less harsh on the grading. If you work in a large group, a very large group, then I'm a little bit more harsh on the grading, a little bit more unforgiving of mistakes, you know, that pop up. Okay. So graded a little bit differently. All right, any other questions on this? On the report? Uh-huh. How many pages? You know, when I first started writing reports, had a hard time writing a lot of pages, and then once you get into research, then you have a hard time not writing a lot. And so a lot of journals, they try to limit the number of pages. They say the maximum number of pages is 15, maximum number of pages is 10, you know, because they don't want it to get too long, too wordy. So you have to end up cutting a lot of stuff and rewording it more concisely. For us, I'm not going to have a maximum number of pages. If you want to write 10 pages, no problem. People have written 10 pages stuff, you know, they like to write a lot. And people have written 2 pages. The shortest report I've gotten is a half a page. The longest report I've gotten is 15 page. The half-page report, you can imagine the grade it got. It was, I think they whipped it together in like 5 minutes before the due date or something. It was awful. But the average report length is about, for the synthesis lab, is about 3 to 5 pages. So, you know, anything in 3 to 5 page range is good. I think shorter than 3 is getting a little too short. And I like single space. You know, I don't like double spaced. Or, you know, you could do a space and a half. That's okay, too. And so 3 pages single spaced is fine. But the thing is, when you're doing single space, you know, there's a lot of blank spaces. Like each time you write an equation, you know, you have to have a blank line and blank line bordering them, right? Each time you write an equation. And there are a lot of equations that you put in here, you know, like the limiting reagent calculation, right? The theoretical yield calculation, the percent yield calculation. All those take up a lot of space. And so 3 pages is not really that much writing when you include all that blank space in there, okay? The figures, whatever else you have in there. And so it's a little thin. And so 5 pages would be better. And it's easy to write a lot of stuff, you know, like those guys were filling up the space talking about isomers and this kind. I mean, what was that? That's like a half page of isomers. After a while, it was getting too much, you know, half page of isomers, but it's easy to fill up the space. You just find something and just start adding more and more details. But where I want the more and more details is maybe something about redox, or maybe something about Lewis acid base, you know, that kind of thing. Or metathesis, or purity, or filtration, or washing. What are you washing out of there? You know, those kinds of things. What are the common contaminants you'd expect in this? Etc. See how long these are. 2, 3, 4, 5, 6. This is 6 pages, including references, and the other one was 5. And so the one was 5 page, the other was a 6 page. Do you have to make a cover page? No. No. One report had a cover page, the other, oh, actually both of these have no cover page. They just have name and then the title and then the abstract. All right, any other questions on this? So this is a good project to start over the weekend, you know, start writing some stuff. All right, I'm going to stop talking here. We're going to start, actually we're going to finish this lab. And so when we finish this lab, I want you to compare your crystals with other people's crystals. Does everybody's crystals look the same? And if they don't look the same, tell me which one's better. And if they look totally different, then did you really make the same stuff? Yeah, just tell me that. Absolutely, you guys don't know, and that's why you have to start searching for stuff. You know, you got to start searching literature, and then find out what is. Does anybody know what this is supposed to look like?